Self video. All right, we're going to start with half-life. Now, I'm probably not going to be talking to the camera a lot today because I am talking to my class because I'm filming this in class. So I've been doing a great job back there. So we're going to talk about half-life, 8th hour. This is just exclusively for you, so we got exclusive video. Let's talk about this. Okay, half-life is going to be dealing with what? What do you guys think half-life is?
A light
video game
of a neutron.
It's a video game. It's a video game that Marilyn's brother plays a lot. Okay. Okay, so half-life, we have radioactive material, right? Okay, so radioactive material is going to ultimately decay. That's the whole purpose of radioactive material. It's going to start with something and decay into something new. Okay, so half-life is the length of time it takes for it to decay into something new. So a really, really common half-life equation is going to be the decay of carbon-14. Now I'm going to make an assumption. Now it might be a big assumption, but I'm going to assume that the majority of you have heard of carbon-14. You may not understand it at all, and that's fine. But carbon-14 as a dating tool, not like Cupid.com or Chemistry.com. No, this is carbon-14 as a dating. It tells how old things are. Has everybody heard of that?
Yeah.
Okay. Yeah. So, carbon-14, they use it to figure out how old things are that have been alive at some point in time. Because what do things that are alive do? They respirate of some sort, or they photosynthesize. So, animals respirate, and plants photosynthesize, correct? They're just the opposite equation. So all of them are going to take in carbon. Once they die, do they take in any more carbon?
No.
No. So they stop, and so whatever they died with is going to be the amount that they have. Carbon-14 is an isotope of carbon, and we know that if you have a certain amount of that carbon-14 left, we can figure out how old you are. So I'm going to show you really quick the equation of carbon-14. Carbon-14 undergoes beta emission, so it gives off a beta particle. And we know a beta particle is 1, -1, or 0, -1. That's not a 1. Kicks off a beta. So what do I make?
14, 6.
Those negative numbers are doozies, aren't they?
12.
7.
Boron.
I'm so sorry.
It's 7. Because 7 minus 1
It's 6.
is 6. Okay, and what is element 7? Nitrogen. Awesome. So what carbon-14 does, carbon-14. Carbon-14 decays into a more stable form. It turns into nitrogen. Okay, and nitrogen, look at your periodic table. Nitrogen has what mass number? 14. So 14 is a fairly stable form of nitrogen, and we know that because the average is really, really close to 14. Does that make sense? Awesome. Okay, so carbon-14, this is an example of a half-life reaction. Let's talk about now how we figure out how long it's been around. I'm not going to go with a really uber-duper tough equation for you. We're going to go really simple here. So we are going to start off with what's called the mother, and then we've got a daughter. And what do you think mothers do? Mothers make
babies.
And that baby is going to be
a daughter.
A daughter. Awesome.
I don't like daughters.
Or a son.
Wait, what?
Okay. So, we always will start with what we have originally. So, this first one, this first little box I've got right here, this first column, we're just going to call that time equals 0. So this is time here. So if time equals 0, how much mother? Let's do percentage before we actually do numbers. Percentages are really easy to work with, right? So if you have all mother and no daughter, how much mother do you have?
100%.
100%.
100% mother.
Okay, so it's 100% mother. So if it's 100% mother, how much daughter is there? 0%. All right. Now, these times, since we don't actually know the amount of time, we're just going to put really simple numbers to make us think here. So this is time equals 0. This is time equals 1 because that represents the first half-life. What if the half-life was 5 years? What number do you think I'd put there?
A 5.
A 5. Okay, so we can always change these numbers up here, but the concept of this is not a half-life. This is how much we start with. This is our first half-life. This is our second, third, fourth, and fifth half-life. Okay. So, after one half-life, how much mother do you think is going to be left?
50.
50.
Ooh, that's deep.
I know, it's crazy, huh? So how much daughter do you think you have now?
50 daughters.
You have 50.
Percent.
Because ultimately, we still need to come up with what number? What number do we have to have here?
100.
We have to represent 100% of what we have, right?
A full life.
Okay,
25.
25.
75.
So the daughter is going to be 75. So at this point, we have 75% daughter. So the majority, we finally stepped into the majority being daughter. Okay, the next one.
12.5.
And that would be 87.5. And then we have what? 6.25. And then we have 93.75. And then we have 3.125 and 96.875. Okay, so we're done. I'm not doing it anymore. That's way out there. Holy cow. But still, we end up adding up to 100%. Okay, that's the whole purpose of what we do. This is half-life. This is how you do half-life. Now there's an equation that I can figure out how to get in between a half-life. I'm not worried about that. That's not one of our outcomes. That's not one of the things that we have to get to. So I'm not worried about it. I'm going to leave that out there for you guys to discover some future day. But I want the concept. The concept is going to be there. Okay, let's work one example problem really, really quick. We're going to work number 12. Okay, so 12 says an isotope of cesium, cesium-137, has a half-life of 30 years. If 1 milligram of cesium-137 disintegrates over a period of 90 years, how many milligrams of cesium would remain? So we're going to start with cesium-137. Now, this doesn't even ask for the daughter, correct? It wants to know how much cesium. So technically, we don't even have to write daughter on this one. But it's still a good habit, at least this early. Let's go ahead and make the daughter on this, just so we get in the habit of doing it. So we don't even know what it turns into, right?
Right.
So who cares? Let's just write daughter. Okay. We will always have a time equals 0. Do not put the length of the half-life in the first one. Don't do it. It'll get you in trouble. So this one's 0. And how long, or how much cesium do I have?
100.
How much?
1 milligram.
1 milligram. How much daughter do I have?
0.
0. Okay, now on this particular one, I actually know my half-lives, right? I know how long it is. So my half-life is 30 years. Since it wants to know all the way to 90 years, I can go ahead and pre-plan. 60 and 90. Because each half-life is 30 years. Some people like to do weird things with these, and they start doing half-life with the time. It's like 30, and then 15, and then 7.5. Don't try to half-life your time. You will get in trouble if you do that. You will end up with all sorts of jacked up answers. Okay, half-life remains constant. So, after 30 years, how much decays? 0.5 milligrams. And how much do I end up making? 0.5. Awesome. So, the next half-life, how much am I going to have?
0.25.
0.25, because it's half of the 0.5. And so that means that 0.5 or 0.25 that got lost has to go down to the daughter. So it's 0.75. Okay? And how much cesium am I going to have after 90 years?
125.
0.125
milligrams.
Okay, so that's our answer. For giggles, we're going to go ahead and write their daughter. And this is 0.875. Okay, not our answer for this one, but still a good thing for us to write at this point. Questions on this?
Those are both 0.5.
How come these are both 0.5?
Because 50.
Yeah, 0.5 and 0.5 are going to add up to 1.
Yeah.
Other questions on this?
Is that it?
Okay, that's it. 8th hour. Make sure you get this worksheet done get it finished up for Monday. So, have a great weekend. We'll see you guys later.
14.
8th hour. Don't get it done for Monday. Get it done for Friday. Friday's tomorrow. I screwed up. I'm sorry. They told me just a second ago. All right.